So our next speaker is Felix Lindner with Apple vs Google Client Platforms. Go ahead.
So, hello, my name is AthCon, and I want to talk to you about mobile client platforms in their respective cloud context. So, we're going to look at two fairly different approaches in client platforms in detail, one being the Apple iPad in the first generation, and the second being the Google Chromebook. And both of those devices are pretty much cloud dependent, so we're going to look at their respective cloud implementations and how they essentially differ. And I want to close with a mobile device security comparison over the four major platforms. So, if you take away one thing from this talk is companies do not make security because they want to, but because they want to protect their business model. So for Apple, most of you probably heard that Apple sold more iPads in the last year than HP sold PC platforms of any kind of form. So every idiot in the world buys iPads. Apple actually makes money from the hardware sales primarily. In 2010, they made 32 billion units sold and 20 billion in US dollars. They take 30% of all money that people make in the App Store, which is another 6 billion, small money. And then they take 30% of everything the mobile provider charges you, phone calls, SMS, data. That's another 2.8 billion US dollars. And this goes to Apple. They have short of 30,000 shareholders, but they're not paying dividends, so it all stays in the company. And this is what they built their security model on. So what Apple wants is, besides the consistent, fluent, simple user interface that everyone loves, what they want is an integrity protection of their operating system. They don't want anyone else on their operating system. They restrict third-party software from the source. You can only get it from the App Store. From the capabilities, like if you're building some software that, let's say, makes a less sucking email client, it will never make it into the App Store because Apple has an email client. They restrict the content and they restrict the payment models. Protecting the user's data is not part of the security design because it's not part of the stuff that they make money with. Accordingly, the Apple App Store is a really restrictive thing. So if you ever try to sign up as an Apple App Store publisher, you will receive a piece of contract that makes every lawyer cry. There is lots of interesting regulations in there. You can get rejected for pretty much any reason. They're not even giving you a reason. And essentially all rights go to Apple, but every possible damage, like damages you can get sued for, are limited on Apple's side to $50. But you already pay $99 to get signed up to the App Store. So essentially it's an out-of-jail-free card for Apple, and all the risk goes to you. Also, they have a very opaque review process. So you're submitting a binary to the App Store. Magic happens. For all we know, they could have a bunch of monkeys tapping around on iPads. And if the monkey farts, then your app is accepted. We really don't know. However, we do know that if the content is not to their liking, let's say it's pornographic or political or Apple bashing, or it's security software, because Apple has no security issues, then it will be rejected. And in their App Store guides, they're so sure of themselves that in their App Store guides, they explicitly say, if you run to the press and trash us, it never helps. So they don't even fear publicity anymore. Now, on the other hand, why does Google make the Chromebook? The goal for Google is data collection. They're generating 96% of all their income from selling user profiles. This is, just a little 30 billion US dollars from ads per year. So here the situation is also very different because 67% of the stock, Class B stock, so of the decision-making and money-making stock, is in the hands of 3 people. So the 3 people make all the money, and everyone else in the company can claim that they're working for a technical company. For that business model to work, Google must actually ensure that the user feels safe to enter his data into the Chromebook so it can go into the Google Cloud and can be used in publishing products. So they have a completely different business reason to build the security model, which actually you already see in the design. So what they want is they want a device that exclusively runs one single program, which is the browser. Not surprisingly, that is Google Chrome. They want to prevent third-party software on a device, so there is absolutely no legal way to put binary code on a device that is not coming from Google. And they actually want to protect the user data, because if the device is stolen, they want the user to get a new device, which is actually fairly cheap. Sign up with his Google ID and everything is nice again. They also want to have a fast startup time. And what is really important, Google realized very, very soon that they have to win over the hearts of the nerds first, because the nerds are the ones that multiply their technology around the other idiots on the planet. So for example, when Google started to have their own public DNS service, even the privacy-loving German hackers would not say, wait a minute now, if I use the Google DNS, then Google knows every single thing I look up and they can profile me even better. What they said was, look at this IP address, it's 8.8.8.8, how cool is that? So they understood this pretty soon. This goes on with their own web store. So Google's web store, you can put extensions to the Google Chrome in there. The sign-up process is trivial, costs you $5, very little contractual hassle, direct submission of the content. There's no review process whatsoever. Everything is HTML and JavaScript anyway, and yeah, there's not much to it. So let's go into the details. The iPad security architecture. So essentially what we're looking at is a standard XNU Mach plus BSD operating system architecture. Everything runs either as kernel root or a single user called mobile. They have a few kernel additions. One is called Seatbelt that limits some things like ptrace debug capabilities. They have binary code signatures, so all the binary code is signed somewhat. We're getting to that. There's a system-wide storage of credentials, so the attacker has a really easy time if they steal your keychain. But there's no on-disk encryption, for example. Like your data sits on disk as it is, and they have ASLR, DP, all the modern shit. They have an integrity protection mechanism. This is common on those client platforms. This is also common for mobile phones, that you have an integrity protection chain, meaning that on power on, there is some initial trust anchor, and from this initial trust anchor, the next stage is validated, and then the next stage is started, and then the next stage validates the third stage, and so on and so on. They're doing this as well. They have in ROM some Apple RSA keys, and they are used for the verification of the next step, and the next step loading LLB, loading iBoot, of course it had an I in it, iBoot loading kernel, checking all the further signatures. Well, this integrity protection is nice if you do it right. This being Apple, they didn't. So essentially, the device can also boot into something that is the DFU mode, device firmware upload mode, right? Yeah, it's unfortunate if you have a buffer overflow in that, which they did, because it's in ROM. So to update the buffer overflow, to fix the buffer overflow, you throw away the device. So yeah, this is how you actually get into any iPad first generation, and this is how all the jailbreaks worked. And then we looked at this bootloader and how it does it in detail, and found out that they are using X509 certificates and a certificate chain from an Apple root CA over some blah blah intermediate CA to entities. And we looked at the code and found out that it doesn't verify basic constraints. Now, short interlude, what are basic constraints? A common use case of an X509 certificate is to build a trust chain, obviously. But obviously, the CA at one point wants to give you a certificate for which you have a private key, but that doesn't make you a CA, right? So essentially, the CA sets a little bit that says, this certificate I'm signing is for a CA or it's not. Now, it's really bad if you're not checking this little bit. Because that means if we have a valid end entity certificate, we can essentially sign shit which eventually is seen as signed by Apple. So we could do that. Interestingly enough, they're actually shipping a private key and a public key and a signed certificate on every single device, which is used for their push services. However, we found out that the bootloader restricts this whole process to 3 steps. And since they had some intermediate CAs already, we couldn't use that vulnerability in the bootloader. However, we looked around in userland and found out that they did the same thing there. Because essentially what they did was they downloaded an open source library called Tomcrypt and used it for all their crypto without understanding the library. So we take this push certificate, push notification certificate, and we sign shit. For example, HTTPS certificates for star, like the entire internet. Or for anything that you do IMAP-S or POP3S or VPN connections or whatnot. And this then caused a very hurried update by Apple. Interestingly here is, so they updated iOS 4, and that means they updated the iPhone 4 and the iPhone 3GS. But nobody else. So if you have an iPhone before 3GS, SSL is broken and Apple doesn't care. Which I find interesting because compare that to Microsoft, who is still shipping security updates for a operating system which is 10 years old and actually out of service, called XP, which actually does SSL correct. So if you have an older device, you want to go to that website, and if you find a nice little lock on top of it, then you're screwed, and you should throw away your iPhone and buy something decent. Coming back to Apple and crypto, they need signature mechanisms to check their binaries, right? I said they have signed binaries. So the kernel verifies the integrity of applications and libraries. But if you do a signature mechanism, don't do it like Apple does, because what they did was they essentially only sign specific sections in the file. They say, well, what's important? The code section, the read-only data section, and this and that. And they essentially leave alone metadata and other things. So what happens is there's obviously a shitload of ways to get around this. For example, they don't sign the header of the file. Well, the header of the file contains the information where the entry point is. So all you need to do is you take a signed binary, you slap some unsigned binary code at the end, you change the entry point to the end, the binary is loaded, everything is happy, and you execute code. Part of the jailbreak me jailbreaks that you find for your iPhone. The system updates for the iPad are essentially covered by the integrity protection and iTunes. So you get application updates in the App Store. However, application updates are also covered by the monkey review process. So if an app developer finds that they have a critical vulnerability in their code and they ship an update in the next hour, it can still take up to 2 weeks or can randomly be rejected by Apple. So there is no shortcut for security updates. Also, one thing that some people want to play with potentially is carrier updates. So the mobile phone carrier can, with some magic, update little things in your iPhone or iPad. For example, the proxy server you're using, which is then an interesting thing if the proxy server is not located at the carrier, for example. So, the Apple App Store, essentially the Apple App Store client and the iTunes Store client are WebKit. So, it's a web browser, and it has a very thin JavaScript wrapper around an Objective-C API containing UIKit classes. It is whitelisted to a certain list of domains, so you can't really say my app store now is at google.com. But the whitelist is pretty permissive, and it has some signed plist XML bullshit. The problem with that whole thing is if you're building a web browser, you should actually build a web browser. So in order for the security assumptions of web browsers to work, for example, the user has to see the address bar. Now, the App Store client doesn't have an address bar because it always talks to Apple, right? But that means the user has no way to see if, it took a left turn and now ran on Google. You have no indicator whether you're using HTTPS or HTTP. And so the standard web security things simply don't cut it anymore because the user can't make educated decisions. That, for example, means that if you inject JavaScript in random Apple websites, let's say in an open waveland like here, you can actually call some of those JavaScript things. Those JavaScript functions contain interesting functions like iTunes.buyAction, which, as you would assume, charges your credit card and buys shit in the App Store. They have CSRF tokens that are meant to prevent attacks that are CSRF based. However, since the libraries are WebKit libraries, they will happily fill in the tokens for you, so the attacker doesn't have to care about them. And this all is pretty hard to fix. So, give you an example. Here is you're in the App Store, as you see. You get a pop-up that asks you for your Apple ID, which is somewhat expected because, you're in the App Store, right? However, this pop-up was actually caused by a little piece of JavaScript that you inject in arbitrary websites, and then, you can guess where the password goes to once you enter that. Certainly not to Apple. Even the vanilla web security things are not right. I already said that the CSRF tokens are not very good. So even if you're blindly injecting, you get like 1 out of 100 shots where it totally worked. The thing is, the whitelist also means, the domain whitelist also means that if we have a cross-site scripting somewhere on a domain that is in a whitelist, we can essentially be the app store for your device. So all we needed was a cross-site scripting somewhere on an apple.com website because they whitelisted entire apple.com. And we looked and we found it on the front page in the search field. Didn't have to look far, did we? So, cross-site scripting in a search field, what? So, essentially, the WebKit has an XSS auditor. It's an XSS client-side prevention tool. And that should actually prevent us from hacking around. However, since this is not a real browser, it will support the data URL or data URI scheme as a source of content, which a sane browser would never do. So there's JavaScript code that we execute in the context of the data origin, which is considered harmless by the browser. And so what we get is we can inject JavaScript that essentially drive-by purchase, download, install, run applications on your Apple devices. This is how you do it. So essentially, the top there is your cross-site scripting thingy, and you put the data URL in there with base64 encoded of the below, and the below essentially buys a stupid piece of shit from the App Store. The interesting thing here is, we were not sure whether we can disclose how to do that because that's a certainly heavy fraud injection issue. And so we talked to Apple how they fix it, and they fixed it by fixing the cross-site scripting in a search field. So if you find another cross-site scripting, feel free to have fun. Now, so how does your data end up in Apple's cloud? Obviously, you will have to switch on, use the iCloud, which very expensive TV advertisements will continuously tell you to do. And also, if you update it over the iTunes interface, if you did an operating system update, you will find that the iCloud is suddenly turned on lately. So what it does is it takes any document that has a certain data type and its URL, any key value file, or any document that in an app subdirectory named documents or library private document, anything in there automatically goes into the cloud. The only thing you can prevent that is, as the app author, you can flag documents as not to be exported into the iCloud, which means you as a user have absolutely zero control over it. It looks like the whole transmission process is HTTPS. We talked about Apple's talent for cryptographic solutions, but let's just assume in dubio pro reo that is secure. But obviously the storage is pretty much guaranteed to be unencrypted, because otherwise Apple wouldn't be able to access your documents and move it to a different device or give it to law enforcement or sell it to someone else. Which, if you read the terms of use, they're totally free to do. So, very good. To quote Stefan Esser, if beer is the answer, I don't care what the question was. Chrome OS security architecture. So essentially, the Chromebook is for people of my age or older that grew up with beating other people for touching their screen. So we prefer to actually have devices with keyboards. But this device is different, so it has a keyboard, but it requires a Google account or a guest account. There's individual separation between the users, so multiple users can use the same device, which is by design, because Google envisions that at some point universities will have Chromebooks, and the student just grabs a Chromebook and uses it with his Google account, and everything goes to Google, and so keep that in mind. It's a standard Linux operating system. They have a few enhancements. They also have one single non-root user ID that they run everything under. They have a very strong focus on preventing native code execution. There is no writable file system that is mounted executable. So they essentially have the equivalent of DEP on the file system implemented. They have a personal firewall, which the iPad doesn't. After we told them that IPv6 is also a protocol that we use nowadays, they added IPv6 to the personal firewall. And what is very interesting, they have automatic silent updates without user intervention. So you can't actually stop the device from updating itself. The only thing that you can access as a user is the Chrome browser. Comes with all the famous features, security features of the Chrome browser, SUID sandboxing, disabled NP API, so you can't actually have binary plugins. It hides the full file system, so if you say file save, you only see your home directory. Interestingly enough, although the Chrome browser ships with Google's own compiled version of Adobe Flash, they apparently forgot to tell Adobe about the file system hiding. So if you have a file save dialog in a Flash application, you see the entire file system. What was funny is, who remembers in 2008 Alexander Sotirov and Posse creating MD5 collision certificates for SSL? Anyone? So most browser vendors fix that by taking the certificate, putting it into the browser and flagging it as evil, so it will never ever be accepted. Google did the same thing but forgot the flagging. So if you're Alex Sotirov and you can control the clock of a Chromebook, you have SSL man in the middle for everything. However, you need the key that only Sotirov apparently has. The device also has a developer mode, so this is appealing to the geeks. I was about to say to the Greeks. It has a small switch on the back of the device. When you then boot the device, it shows you a scary big screen. Wow, you're in developer mode, careful, blah, blah. They also have an integrity protection chain. It is a lot more solid than the one that Apple developed. This here is actually from their documentation. What you see here, there's firmwares and kernels. So the way they built the system is actually not too stupid. They have a ROM section, then they have a firmware, then they have a kernel, and then they have the file system. And of all of them, they have two. So if they're updating one site and they fuck it up, they can still switch over to the other one. So everything is redundant. Key material stuff, this all works essentially. What is funny is they actually use the TPM on the platforms to check that you don't use an older key, so you can't do a rollback attack if you manage to crack an older Google key. So you can't really use that because it has seen a newer key. What it also factors in is the kernel version. So if anyone here can convince Linus Torvalds to adopt the versioning strategy of Firefox, so every 2 weeks we get a new major version of the Linux kernel, because if and this is a 16-bit field, so if we manage to get the Linux kernel major version to 65.535, all Chromebooks stop working forever. So if you know Linus Torvalds, it might be worth to give him a drink or two and convince him to do that. They built an extremely smart and fast file system integrity checking. Because what they do, like if you build embedded systems, this is how you do it. They don't integrity check the file system, they integrity check the actual hardware layer, like the actual hard drive. The whole partition is checked every single block by a hash, and then there is a super hash on top of that. So essentially every time you read a block from the partition, it will have this verified list of hashes, and it will check the hash of this block, and if it matches, fine. If not, you get a little sign that says, please connect me to the internet, and I want to reinstall myself. This is actually extremely smart because caching kicks in on a layer above that, so you're not verifying a block twice in most cases. And this brings your boot up time, for example, down to less than 10 seconds and makes it really, really portable. However, even that integrity protection has imperfections. For example, the partition table is not integrity protected. So if you can make the kernel or kernel driver write into the partition table, it will fuck up parts of the device. There's also partitions for OEM stuff or EFI modules that are not integrity protected. So the assumption is with later Chromebooks that if you can write into the EFI section, you can load EFI modules before even the Linux kernel starts and backdoor it that way. And there's a theoretical breach of integrity here, because at the point where they're starting the kernel, this is what they have as the integrity as the start parameters for the kernel. And what you see here in red is the %u+1. This is where they later fill in the UIDs of the disks that they actually want to boot. But the thing, of course, is the upper one is what they signed, and the lower one is what they execute. So this is obviously a theoretical breach. I've seen a talk submission to a conference in Asia where some academics claim that they could actually turn this into an actual attack. I would love to see that. I was simply too dumb to do it. When you keep in mind that the books are meant to be shared, like in universities, it is also worth noticing that this read-only section in the beginning, where they have the root key, which then loads the firmware, is obviously somewhere on a chip. And one of my colleagues found out that you essentially connect two little pins in the device, and that makes the read-only less read-only. Essentially, you can run software and say, please become read-write, and it will say yes. And then you update the firmware loader, and so we do have a Chromebook now that says Recurity Labs when you boot it. Which obviously means that you can then essentially do whatever you want, backdoor the kernel, whatever. The Chrome OS user data encryption, the home directory encryption, is a pretty well-designed crypto system from my point of view. I'm everything but a crypto expert. What is interesting here for you to note is that it essentially depends on your user password. So this is fairly decent data separation, because one user cannot access the home directory of the other user because he doesn't have the key. The key is generated based on your user password that you enter. So this is important to keep in mind. The update story with the Chromebooks is a bit strange. As I said, it does not allow user intervention. Every 45 minutes, it talks to Google using Google's Omaha protocol. And then it starts taking the active system partition, and it runs a update on the inactive system partition. The updates are incremental modifications of the firmware and root partitions. So essentially, Google has to have a consecutive history of every single image they ever shipped. If they ever lose one, the update is not going to work, because they're also updating the hashes for the block tables. The update is transported over SSL and is by itself integrity protected. What is again interesting here is a fairly brave approach. The integrity protection is checked after the update is applied. So they're not downloading the whole update, check the integrity, and then apply the update. No, they download the update step by step and applying it to the other partition. And at the end, they do the hash and go like, whoops, something was wrong, or yes, it was good. And the only thing they do, the signaling something was wrong or good, is whether they set the bootable flag for the other partition back or not. If you now keep in mind that the partition table is not integrity protected, there is again a theoretical way to get in there, but we couldn't make it practical. I should call it some loft guys. They made it theoretical practical since 1987 or something, right? Okay, so the Google Web Store, as I said, is the version of the App Store, distributes browser extensions. It's all JavaScript stuff. The user grants permissions on installation, we all know that. What is interesting here, the API itself, like what a Chrome extension can do, is essentially, it looks like it was built for Russian banking Trojans. Because one thing you can do is a so-called content script, where you say, for the following domains, I would like to get control after you rendered the entire DOM, and I would like to change some things in the DOM. Which is exactly what very expensively made banking Trojans on Windows usually do, so that they can get your PIN and your tons and whatnot and send it to servers outside your bank's domain. So it's really, really powerful. We already see submissions for Black Hat Vegas that make an entire talk about it. They also have paid extensions so that people can make money off their browser extensions. But they're not really well protected, so if you have the extension ID, which you see when you browse the catalog, you can essentially create a certain request here, and then you download the extension for free. You can also use the Google Sync configuration for your browser and just add the ID to the configuration, and next time you sync your browser, it will download the extension for you, without you paying, obviously. What we found interesting, and what comes back to my initial point, keep in mind what they make the money with. When we reported this to Google in an actual on-site meeting, they said, oh, that's bad, we should update the documentation. So they have no interest in protecting the poor people that make money off a few extensions that they sell on the Google checkout, because that's not what they make money with. They rather document the fact that this protection simply doesn't work. Certainly cheaper. How can you install malicious extensions in browsers? Well, obviously if you get control over the Google account, you can use Google Sync and just add the malicious extension to it. Google also exposes in Chrome special APIs to the web store. They had an issue, what we found, that they had HTTP domains within their whitelist, so you could inject HTTP. Very similar to Apple, and have them download and install extensions. The confirmation dialog that says, yes, I want to install that, was implemented via JavaScript. So the extension could click itself on the dialog and say, yes, install me. And as I mentioned, the malicious extensions are fairly powerful. You essentially control the browser in an extent that you cannot imagine in Firefox or IE. Now, let's move into the Google Cloud. So an example here being Google Apps. So for the Google Apps game, you have to realize that if your account is compromised, everything is lost. If your session cookie is compromised, your account is compromised. So a better password or two-factor authentication doesn't help you that much, because you have to lose this fucking cookie once, and that's it. If Google doesn't love you anymore, let's say because your name doesn't sound correct on Google+, you're fucked. Or if someone else can make Google not loving you anymore, law enforcement, governments, so on, you're fucked. If you keep that in mind, fine, you can use Google Apps. So essentially your protection must cover the authentication and authorization of the user and third-party applications. There are many Google apps that use some third-party code, and this is an actual nightmare because Google keeps buying companies. And integrate their products in their offerings, and often this code is really not compatible with the way Google does stuff, so they hand over cookies back and forth. At some point you can see people, see apps handing like 30 cookies from one side to the other because they couldn't make up which cookie is the important one now. So there's certainly hack value, and since nowadays they're paying lots of money if you find critical bugs, this is where you should look. An example of interesting things in the cloud, Google Docs allows to write macros for their spreadsheet applications. Those macros are actually executed on Google servers. You can import macros from other people, which, once you look at the code and then you say, this macro is cool, and you say, okay. If the other guy updates the macro later, it might change behavior. What we found really interesting, one of the leading macros used by the most people on Google Docs is a credit card number validation checker by a Russian. And it's actually legitimate. It's actually not stealing stuff. So it's the one Russian that gets a shitload of credit card numbers and not misuses them. I found this good. But as I said, like, if he ever turns sites, then everyone is fucked. What is also interesting is the macros can do HTTP requests. Now keep in mind those HTTP requests come from within Google. You can get up to like 50 gigs per second data transmission within the Google data center. So only Google can actually DOS Google. And that's a pretty decent way to do it. We found one way where the actual account switching functionality on the Google main site would actually allow you to steal someone else's account. I'm not walking you through the entire process, but essentially you intercept a login request and you present an account switch request where you are already logged in, and then the login becomes an account switch for the user, and it looks similar, not 100% equal to regular Google login, but very similar, and you end up having the cookie, which then is obviously game over and should actually be fixed by now. Well, even Google belongs to the companies that still think that OWASP top 10 is something to achieve. I think some managers obviously have in their yearly review, do OWASP top 10. Cross-site scripting, check, yay! So also Google sites have cross-site scripting. The Google Sites part is actually a very interesting playground if you want to get paid by Google for vulnerabilities. Google Sites is a good starting point because you're living off a google.com domain, which breaks same origin pretty nicely, and you have a lot of power over what you can do. Other services have lots of 90s style cross-site scripting issues. So, for example, the administrator panel in Postini, the secure and encrypted Google email service that is also used by many government agencies in the States, actually has a cross-site scripting bug when viewing messages from users. So if you have a cross-site scripting in a subject of an email of a user, you call the admin, say, look at this account, please, and plop, admin gets owned. And this whole authorization and exchange of data thing really doesn't work too well even on Google's side. An example being, if one site wants to access your data in Google Apps, you get a little website from Google that says, well, do you want to allow eve.com to go and steal your data? What you can obviously do is you use a little redirect where you automatically essentially click on the I feel lucky button, which then causes Google to ask you something like this. Google wants to access your Google account. Do you want to allow this? Well, the obvious answer is, well, you already fucking own my data, so go ahead, which then redirects through the search engine and the I feel lucky onto our web server and happily leaks your authorization token into our web logs. So what you see here is the Google summary is essentially Google succeeded in hardening the client platform in order to make the user feel this is really safe and I can enter my data here. What in fact happens is you're moving the risk into the cloud, where the security challenges are still a lot harder, and even almighty Google makes mistakes in the form that, like, we learned how to do shit right many years ago, but in cloud computing we throw away this knowledge and begin anew as if nothing happened. Also, clouds are pretty opaque, so a collection, I pieced the following together, so this is rumors, but I talked to a couple of people independently and found out the following interesting thing. Apple runs the iCloud, not themselves, but they run it on Google and Microsoft. Now, Google actually runs his cloud now in IBM data centers, largely for the non-essential services. IBM, that I know for a fact, actually runs their data centers not themselves anymore, but outsource them to third parties and have them operated by people in China. What?
I can't say much about where Google's running the data centers, but I can deny that a large portion of these runs on their base.
So I said it's rumors. So, but the core of the problem being, you never know where your data ends up at and who's actually responsible. So if you have a data breach in this scenario, who was it? Like, who do you sue? So I want to close with what I find an amusing matrix of the four major mobile platforms nowadays. So you have the four major platforms. You will see that the two widely used platforms actually run native code, while the BlackBerry and the almost not used Windows Phone actually only allow managed code. The permission model for the apps is pretty much the same on all of them. So when you install an app, it gives you a menu of stuff it wants to do with your data, and either you're fine with that or you don't get the app. That's the same for everyone. Device management is very different across the board. So the Apple iOS has some device management, but is unfortunately pretty undefendable. On Android, you have nothing that comes from itself. There's a lot of third-party products, but not by itself. BlackBerry and Windows Phone actually have device management. They all have somewhat of a cloud. You could consider the BlackBerry Enterprise Service as a private cloud. But now, the interesting part is the vulnerabilities on iOS and Android, we have plenty. BlackBerry introduced WebKit, so it made it hackable from unhackable. On Windows Phone 7, so far, the only thing that broke were OEM extensions. And the most amusing, remember in the 90s, we Linux users were making fun of the Windows users for having all the malware. On the mobile phones, now the Windows Phone users make fun of the Linux Android users for having all the malware. And with that, I think I want to close, and thank you for your attention. Any questions? Beer?
In order to make money, essentially.
Oh, I was just pointing out possibilities, but also the media is not a very good measure for that. You don't have to take my word. Go and look up the stories of reporters that critically cover Apple in the media and what happens to their careers. Insofar, the media is not a very good measure on what actually happens.
Do you think that will the iCloud idea ever be safe in any implementation?
Well, I think so far there is no business incentive in doing it correctly. The whole point of running a cloud is to have access to your users' data. I'm pretty sure that with moderate brain power investment in cryptography solutions that encrypt on the client side, you could actually make a halfway decent cloud that has opaque storage, or even calculation. There's advanced cryptographic concepts that I'm not really understanding, but apparently it is possible to actually run calculations and operations on encrypted data without having the key. The problem is there's no business incentive of doing so.
When you mentioned, I guess speaking about the iPhone or iPad, iOS, you was mentioning that basically the same origin policy is not respected, but they're using WebKit by default, right? So it should be respected. I don't know, I mean, can you elaborate on that?
The question is, it was in the context of the App Store application and the iTunes application.
Okay.
But even if you use WebKit, that's one thing. But you actually have to implement the hooks that make the same origin policy checks, and you have to actually turn them on. And in in the App Store app, for example, they're simply turned off because they assume that whoever they talk to is always Apple, and the origin doesn't play a role. So you can turn it off, and that's what they did. Okay, thank you very much, then.